Hello? Hello?
Yes, Aditya, speak.
We will start the quiz now.
Yes, Aditya.
Is the screen visible?
Hello, very good evening, everyone. And I hope, am I audible?
Yes, Vedant, you are audible. Yes, yes, yes. Yes, yes,
Okay,
Vedant.
good, good. So, good evening, everyone, and congratulations, Vidhushi, Bhavya, and I'm sorry, I just missed the third name. Um can you go back to the podium, please? And okay, Bhavya, Vidhushi, and the second name, Harika. So we got new names this time, I guess. These are not the one which were there in the first quizzes before. And well, in no time we have already covered 1 month of this program. We have completed week 4, and 1 month at SheCodes has already been done. And for me, I don't feel like that happening. I mean, I know you guys have worked a lot completing all the modules, and maybe you must be feeling like it's like 2 months. But for me on this side, I feel like the time just flies away. And congratulations for completing 1 month with us. And we are very excited for the coming weeks at SheCodes because it's going to be exciting. Just 2 months of learning left, I guess, like 2 weeks of learning left, I guess, and then we'll have the exams, those things. Well, I hope you enjoyed today's quiz. And next, we have exciting session by Miss Medhasweta Sen. I'm very sorry about the misspelling of your last name. It's Medhasweta Sen, not Bain. And she's participant at SheCode, but along with that, she's expert in statistics. She's doing bachelor's in statistics, and we were very excited to have her as um, presenter today, and she'll be telling us about what are some of the statistical methods used in data science, some correlation between data science and statistics, what are proposed learning path, and much more about in this domain. So, hi, Medhasweta.
Hi.
Can you hear me?
Yes, I can.
Okay, so we are very excited today to have you here. And I went through the slide deck. I had a sneak peek, and it's really very insightful. So I'm very excited for this session, and I guess that's the same for all of us here today. I hope you have option for share screen.
Yes, I do.
Okay, great. So let us know whenever you are ready.
Yeah, I'll start sharing now.
Yeah, sure.
Is it visible?
Yeah.
Okay, so I'll start.
Okay, good luck. Thank you.
Thank you. Hi, I am Medhasweta Sen, a second year statistics honors student at Lady Brabourne College, Kolkata. It is my great privilege to be provided with the opportunity to have this session. The topic of this session is statistics for data science. I'll begin with a brief introduction of statistics. So, what is statistics? Statistics is a form of mathematical analysis that uses qualified models, representations, and synopses for a given set of experimental data or real life studies. Statistics studies methodologies to gather, review, represent, analyze, and draw conclusions from data. It is considered as a mathematical body of science that deals with data. Some consider statistics to be a distinct mathematical science rather than a branch of mathematics. While many scientific investigations make use of data, statistics is considered to use data in the context of uncertainty and decision making in the face of uncertainty. In order to understand the purpose of statistics, we need to briefly look at the history and origin of statistics. The mathematical foundation of modern day statistics were laid in the 17th century with the development of probability theory by Gerolamo Cardano, Blaise Pascal, and Pierre de Fermat. Mathematical probability theory arose from the study of game of chance. Although the concept of probability was already examined in the medieval law by philosophers like Juan Caramel. In the 18th century, the rise of inferential statistics was seen with the publishing of Jacob Bernoulli's The First Derivation of the Law of Large Numbers, Abraham de Moivre's introduction of the normal distribution to approximate the binomial distribution with probability, Thomas Bayes' proving of Bayes' theorem, and Playfair's commercial and political atlas introducing graphs and bar charts of data for the first time. In the 19th century, Adrien Marie Legendre introduced the method of least squares for fitting a curve to a given set of observations. Quetelet's treatise on man introduced social science statistics and the concept of average man. Wayne's logic of chance defended the frequency interpretation of probability. Charles outlined the frequentist statistics, emphasizing the use of objective randomization in experiments and in sampling. Thiel gave a mathematical analysis of Brownian motion, introduced the likelihood function, and invented cumulants. Bachelier analyzed stock price movements as stochastic processes. In the 20th century, Peirce invented an optimally designed experiment for regression. Galton introduced the concept of correlation. Keynes' treatise on probability defended a logical interpretation of the probability. Wright developed path analysis. Tippett and Fisher introduced extreme value theory. Neyman introduced the concept of confidence interval in the statistical testing. Cox's theorem derived the axioms of probability from simple logical assumptions. Shannon's mathematical theory of communication defined the capacity of communication channels in terms of probability. The 21st century has witnessed a large amount of research dedicated to the teaching and implementation of statistics in various walks of life. The impact of this research has started to change the course and content and the structure in both introductory and advanced courses for statisticians and those from other disciplines. In the light of these changes, future directions in teaching and learning of statistics must take into account new innovative academic instructions and educational technologies. Statistics can be broadly classified into two distinct branches, namely descriptive statistics and inferential statistics. Descriptive statistics deals with the representation and collection of data. It is usually the first part of statistical analysis. It is usually not as simple as it sounds. The statistician needs to be aware of designing experiments, choosing the right focus group, and most importantly, avoid biases that are so easy to creep into the experiment. Inferential statistics, as the name suggests, involves drawing right conclusions from the statistical analysis that has been previously performed using descriptive statistics. In the end, it is the inferences that make the study important, and this aspect is dealt with in inferential statistics. Though some of the statistical measures used in both the branches are very similar, but the goals and methodologies for the two are very different. Descriptive statistics, on one hand, is used to summarize and graph the data for a group that is chosen. This process helps understand the specific set of observations. One can simply take a group that they are interested in, record the data about the group members, and then use summary statistics or descriptive statistics and graphs to present the group properties with descriptive statistical tools. In descriptive statistics, there is no uncertainty as it is describing only the people or the items that is actually being measured. No inference whatsoever is made about the properties about a larger population. The process involves taking a potentially large number of data points in the sample and reducing them down to a few meaningful summary values and graphs. This procedure allows gaining more insight and visualizing the data. So it is more likely to get definitive calculation using descriptive statistics. In other words, descriptive statistics only measures the group one assigns for the experiment, meaning that one decides to not factor in the variables. Inferential statistics, on the other hand, takes data from a sample and makes inferences about the larger population from which the sample was drawn. Because the goal of inferential statistics is to draw conclusions from a sample and generalize them to a population, one needs to have confidence that the sample accurately reflects the population. This requirement affects the process. At a broad level, one must follow the following steps to do so. 1. Define the population being studied. 2. Draw a representative sample from the population. 3. Use analysis that incorporates the sampling error, which may lead to additional tests to be conducted on the larger population depending on how much data is needed. It is to be kept in mind that one does not pick a convenient group. Instead, random sampling allows having confidence that the sample represents the population. This process is a primary method of obtaining sample that mirrors the population on average. Random sampling provides statistics such as mean that do not tend to be too high or too low. Using random sample, one can generalize from the sample to a broader population. Unfortunately, gathering truly random sample can be a complicated process, but it is easier to come up with conclusions in inferential statistics than in descriptive statistics. Role and significance of statistics in other walks of life. I have previously discussed that the 21st century saw the use of statistics in various other fields. It plays an important role in every field of human activity. It holds a central position in almost every walks of life. These roles have been elaborated in the following slides. In physics, statistics is used in the following ways. Astrostatistics. It is the discipline that applies statistical analysis to the understanding of astronomical data. Statistical thermodynamics. It is the study of the microscopic behaviors of a thermodynamic system using probability theory that provides a molecular level interpretation of thermodynamic quantities such as work, heat, free energy, and entropy. Statistical physics. It is one of the fundamental theories of physics and uses methods of probability theory in solving physical problems. Statistical mechanics. It is the application of probability theory that includes mathematical tools for dealing with large population to the field of mechanics, which is concerned with the motion of particles or objects when subjected to force. In chemistry and geology, statistics is used in the following ways. Chemometrics. It is the science of relating measurements made at a chemical system or process to the state of the system via application of mathematical and statistical methods. Geostatistics. It is a branch of geology that deals with the analysis of data from disciplines such as petroleum geology, hydrogeology, hydrology, meteorology, oceanography, and geography. In biology, environmental science, and medical sciences, statistics is used in the following ways. Biostatistics. It is the branch of biology that studies biological phenomena and observations by means of statistical analysis and includes medical statistics. Population ecology. It is the subfield of ecology that deals with the dynamics of a species or a population and how these populations interact with the environment. Environmental statistics. It is the application of statistical methods to environment science. Weather, climate, air, and water quality are included as studies of plant and animal populations. Epidemiology. It is the study of factors affecting the health and illness of population and serves as a foundation of logic, and intervention is made in the interest of public health and preventive medicine. Psychometrics. It is the theory and the technique of educational and psychological measurement of knowledge, abilities, attitude, and personality trait. Quantitative psychology. It is the science of statistically explaining and changing mental processes in behaviors in human. In justice and criminology, statistics is used in the following ways. Forensic statistics. It is the application of probability models and statistical technique of scientific evidence such as DNA evidence and the law. In contrast to everyday statistics, to not engender bias or unduly draw conclusion, forensic statisticians report likelihood or likelihood ratios as LRs. Jurymetrics. It is the application of probability and statistics to law. In engineering, statistics is used in the following ways. Reliability engineering, it is the study of the ability of a system or component to perform its required functions under stated conditions of a specified period of time. Machine learning, it is the subfield of computer science that formulates algorithms in order to make predictions from data. In economics, finance, and manufacturing, statistics is used in the following ways. Business analytics, it is a rapidly developing business process that applies statistical methods to data sets, often very large, to develop insights and understanding of the business performance and opportunities. Demography, it is the statistical study of all populations. It can be a very general science that can be applied to any kind of dynamic population, that is one that changes over time and space. Econometrics, it is a branch of economics that applies statistical methods to the empirical study of economic theories and relationships. Operations research or operational research. It is an interdisciplinary branch of applied mathematics and formal science that uses the method of mathematical modeling, statistics, and algorithm to arrive at an optimal or near optimal solutions to complex problems. Quality control, it reviews the factors involved in the manufacturing and production process. It can make use of statistical sampling of product items to aid decisions in the process control or in accepting deliveries. Statistical finance, an area of econophysics. It is an empirical attempt to shift finance from its normative roots to a positivist framework using exemplars from statistical physics with an emphasis on emergent or collective properties of financial market. Statistical signal processing. It utilizes a statistical property of signals to perform signal processing tasks. Actuarial science, it is a discipline that applies mathematical and statistical methods to assess risk in the insurance and finance industries. Now, in order to understand the relationship between statistics and data science, we need to define and understand what is data science. This brings me to my next subtopic, what is data science? Data science is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insight from many structured and unstructured data. Data science is related to data mining, machine learning, and big data. It is also defined as the concept to unify statistics, data analysis, and their related methods in order to understand and analyze actual phenomena with data. It uses techniques and theories drawn from many fields within the context of mathematics, statistics, computer science, domain knowledge, and information science. Turing Award-winning Tim Gray imagined data science as a fourth paradigm of science, empirical, theoretical, computational, and now data-driven, as asserted that everything about science is changing because of the impact of information technology and the data deluge. The term data science was for the first time coined in 2008 by DJ Patil and Jeff Hammersbacher, the pioneer leads of data analytics effort at LinkedIn and Facebook. A brief history of data science. Although data science isn't a new profession, it has evolved considerably over the last 50 years. A trip into the history of data science reveals a long and winding path that became as early as 1962 when mathematician John W. Tukey predicted the effort of modern-day electronic computing on data analysis as empirical science. Yet data science of today is a far cry from the one that Tukey imagined. Tukey's predictions occurred well before the explosion of big data and the ability to perform complex and large-scale analysis. After all, it wasn't until 1964 that the first desktop computer, Programmer 101, was unveiled to the public in New York World's Fair. Any analyses that took place were far from rudimentary than the ones that are possible today. By 1981, IBM had released its first personal computer. However, it would take nearly 2 decades before they could start to convert their data into information and knowledge. Throughout the 2000s, various academic journals began to recognize data science as an emerging discipline. In 2005, the National Science Board advocated for data science as a career path to ensure that there would be experts who would successfully manage a digital data collection. By this time, companies had begun to view data as a commodity which they could capitalize. In 2010, all of that started to change as data science began to take a center stage against the backdrop of significant advancements in computing technology. With faster processing speed than ever before, technology took a giant leap into the new decade, blazing a trail of individuals ready and willing to conquer the mountain of big data that had already begun to grow. Over the last 6 years, data science has continued to evolve and permeate nearly every industry that generates or relies on data. Today, data scientists are invaluable to every company, and data science degree programs have emerged to train the next generation of data scientists. Increasingly, data scientists are also drawn from a variety of different academic and professional backgrounds, including health, computer science, and psychology. Data science and its applications will only continue to grow. That's because big data will get even bigger. Role and significance of data science in other walks of life. The top data science applications are in the fields of banking. Banking is one of the biggest applications of data science. Big data and data science have enabled banks to keep up with the competition. With data science, banks can manage their resources efficiently. Furthermore, banks can make smarter decisions through fraud detection, management of customer data, risk modeling, real-time predictive analysis, customer segmentation, etc. Banks also assess the customer lifetime value that allows them to monitor the number of customers they have. It provides them with several predictions that the business bank will derive through their customers. In case of fraud detection, banks allow the companies to detect frauds that involve a credit card, insurance, and accounting. Banks are also able to analyze investment patterns and cycles of customers and suggest them several offers that suit them accordingly. Furthermore, banks have the ability to risk modeling through the data science through which they can access their overall performance. With data science, banks are able to tailor personalized marketing that suits the need of their clients. In real time and predictive analytics, banks use machine learning algorithms to improve their analytic strategies. Furthermore, banks use real time analytics to understand underlying problems that impede their performance. Finance. Data science has played a key role in automating various financial tasks. Just like how banks have automated risk analytics, finance industries have also used data science for this task. Financial industries need to automate risk analytics in order to carry out strategic decisions for the company. Using machine learning, they have identified and been able to monitor and prioritize their risks. These machine learning algorithms enhance cost efficiency and model sustainability through training on a massively available customer data. Similarly, financial institutions use machine learning for predictive analytics. It allows the companies to predict the customer lifetime value and the stock market moves. Data science also plays a key role in the algorithmic training. Although rigorous analysis of data, financial institutions are able to make data-driven decisions. It is also playing an important role in making the customer experiences better for the users. Through extensive analysis of the client experience and modification of preferences, financial institutions are able to create personalized relationships with their customers. This is further boosted by real-time analytics of the customers, which increase personalization and the profitability of the business. Manufacturing. In the 21st century, data scientists have often been known as the new factory workers. This means that data scientists have acquired a key position in the manufacturing industries. Data science is being extensively used in the manufacturing industry for optimizing production, reducing cost, and boosting the profits. Furthermore, in addition with technologies like Internet of Things, IoT, data science has enabled the companies to predict potential problems, monitor systems, and analyze the continuous stream of data. Furthermore, with data science, industries can monitor their energy costs and can also optimize their production hours. With with a thorough analysis of customer review, data scientists can help the industries to make better decisions and improve the quality of their products. Transport. Excuse me. Another important application of data science is transport. In the transportation sector, data science is actively making its mark in making safer driving environments for the drivers. It is also playing a key role in optimizing vehicle performance and adding greater autonomy to the drivers. Furthermore, in transport sector, data science has actively increased its manifold with the introduction of self-driven cars. Through an extensive data analysis of fuel consumption patterns, driver behavior, and active vehicle monitoring, data science has created a strong foothold in the transport industry. The self-driving cars, the most trending topic in today's world. With the introduction of autonomy, the vehicles through reinforcement learning, vehicle manufacturers are able to create intelligent automobiles. Healthcare. In the healthcare industry, data science is making great leaps. In various industries in healthcare, making use of data science are in medical image analysis. In medical image analysis, data science has created a strong sphere of influence for analyzing medical images such as X-rays, MRI, CT scans, etc. Previously, doctors and medical examiners would have to manually search for clues in the medical images. However, with the advancement in computing technologies, search and data, it is possible to create machines that can automatically detect flaws in the imagery. Data scientists have created powerful image recognition tools that allow doctors to have an in-depth understanding of the complex medical imagery. Genomic data science. Genomic data science applies statistical techniques to genomic sequences, allowing the understanding of the defects in genetic structure. It is also helpful in classifying diseases that are genetic in nature. With data science, we can analyze how genes react to varying kinds of medicine. Also, several big data technologies like MapReduce have significantly reduced the processing time of genome sequencing. Drug discovery. Another important field making use of data science is drug discovery. In drug discovery, new candidate medicines are formulated. Drug discovery is a tedious and often complex process. Data science can help us to simplify this process and provide us with early insight into the success rate of newly discovered drugs. With machine learning, we can also analyze several combinations of the drugs and their effects on different gene structures to predict the outcome.
Hello.
Yeah.
Uh, just a minute. Yeah. Everyone, please unmute yourself.
E-commerce. E-commerce and retail industries have been hugely benefited by data science. Some of the ways in which data science has transformed the e-commerce industries are by identifying a potential customer base. Data science is being heavily used. Usage of predictive analytics for the forecast of goods and services. Data science is also used for identifying styles of popular products and predicting their trends. With data science, companies are optimizing their pricing structures for their customers. This brings me to my next subtopic. What is the difference between data science and statistics? The key differences between data science and statistics are: number one, data science combines multidisciplinary fields and computing to interpret data for decision making, whereas statistics refers to mathematical analysis, which use qualified models to represent a given set of data. Number two, data science is more oriented to the field of big data, which seeks to provide insightful information from huge volumes of complex data. On the other hand, statistics provides methodology to collect, analyze, and make conclusions from data. Data science uses tools, techniques, and principles to sift and categorize large volumes of data into proper data sets or models. This is contrary to the statistics, which confines itself with tools such as frequency analysis, mean, median, variance analysis, correlation and regression, and so on, to name a few. Data science will investigate and inspect data to deduce factual, quantitative, and statistical inferences. This is opposed to statistics, which focus on analysis using standard techniques involving mathematical formulas and methods. Our data scientists must have skill sets to analyze and simplify problems using complex data sets to figure out information, whereas a statistician will use techniques of numeric and quantitative data analysis. Role of statistics in data science. Now, before I get into the proper role of statistics in data science, this Venn diagram shows what data science essentially consists of. And please take a look at this Venn diagram. This is actually pretty self-explanatory. So, the role of statistics in data science. Statistics and probability is the base of data science. One should know the fundamentals and concepts so as to solve the data science problems. Data science and statistics is an indistinguishable and closely linked fields. It is clear that statistics is a tool or method for data science, whereas data science is a wide domain where statistical methods is an essential component. Data science and statistics will continue to exist, and there is a big overlap between the two disciplines. Also to note, all statisticians cannot become data scientists and vice versa. Data science has developed recently with big data and will continue to grow in the coming years as data growth seems never ending. It is often said that a data scientist is a better statistician than any programmer and a better programmer than any statistician. This brings me to my next subtopic. How is statistics used in data science? The statistical methods used in data science can be broadly classified under two heads: descriptive statistical tools and inferential statistical tools. Descriptive statistical tools as used in data science are a measure of central tendency. A measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within the set of data. Such measures of central tendency are sometimes called measures of central location. They are also classified as summary statistics. Some of the common measures of central tendency are arithmetic mean, the sum of all the measurements divided by the number of observations in the dataset; geometric mean, the nth root of the product of the data values, where there are n of these. This measure is valid only for data that are measured absolutely on a strictly positive scale. Harmonic mean, it is the reciprocal of the arithmetic mean of the reciprocals of the data values. This measure too is valid only for data that are measured absolutely and strictly on a positive scale. Mode is the most frequent value in a data set. This is only a central tendency that can be used with nominal data, which is purely qualitative category assessments. Median. The median is the middlemost value that separates the higher half from the lower half of the data set. The median and the mode are the only measures of central tendency that can be used for ordinal data, in which the values can be ranked relative to one another but cannot be measured absolutely. Second is the measures of dispersion. In statistics, dispersion, also called variability, scatter, or spread, is the extent to which a distribution is stretched or squeezed. Some examples of measures of statistical dispersion are variance, standard deviation, interquartile range. Dispersion is contrasted to the measure of location or central tendency, and together they are the most used properties of distribution. A measure of statistical dispersion is a non-negative real number that is zero if all the data are the same and increases as the data becomes more diverse. Most measures of dispersion have the same unit as the quantity being measured. In other words, if the measurements are in meters or seconds, so is the measure of dispersion. Some definitions of the previously mentioned measures of dispersion are: interquartile range or IQ, or the difference between the 75th and the 25th percentile, or between the upper and the lower quartiles, and range is the difference between the largest and the smallest values in the data set. Also, standard deviation is the square root of variance. Skewness and kurtosis. Skewness is the measure of asymmetry of the probability distribution of a real valued random variable about its mean. The skewness value can be positive, zero, or negative, or undefined. Kurtosis is a measure of the tailedness of the probability distribution of a real valued random variable. Like skewness, kurtosis describes the shape of the probability distribution, and there are different ways of quantifying it, for a theoretical distribution, and corresponding ways to estimate it from a sample population. Different measures of skewness and kurtosis may have different interpretations. Graphical method of data representation. Graphic representation is a way of presentation of data and information. Usually graphs are used to present time series and frequency distributions. It is known as data visualization in data science. The types of graphs are: time series graph. A time series graph depicts the value of a variable over a different point of time. This is a time series graph. In a time series graph, time is most important factor and the variable is related to time. It helps in understanding and analysis of changes in variables at different points of time. Many statisticians and businessmen use these graphs because they are easy to understand and also because they offer complex information in a very simple manner. Line graph. Line graph is used to summarize how two pieces of information are related and how they vary with one another by joining the various points on the graph with a straight line. Histogram. A histogram is a graph of group frequency distributions. In a histogram, we plot class intervals on x-axis and their respective frequencies on y-axis. Further, a rectangle is created on each class interval with the height proportional to the frequency density of the class. Frequency polygon. A frequency polygon is another way of representing a frequency distribution on a graph. We draw a frequency polygon by joining the midpoints of the upper width of the adjacent rectangles of the histogram with straight lines. Frequency curve, with the vertical of the polygons are joined with a smooth curve, and then the resulting figure is called a frequency curve. The number of observations increase the need to accommodate more classes. Therefore, the width of each class reduces. In such a scenario, the variable tends to become more continuous and the frequency polygon starts to take the shape of a frequency curve. Cumulative frequency curve, or ogive. A cumulative frequency curve, or ogive, is a graphical representation of the cumulative frequency distribution. Since a cumulative frequency is either of the less than type or the more than type, ogives are of two types: the less than ogive or the more than ogive. One of the most important kind of graphs is the scatter plot. The scatter plot is a very simple graph in which the x and the y axis of the bivariate data set is plotted, and this helps us to understand the or even on an average guess the kind of regression relation that exists between the x and the y axis of the various data sets of a bivariate value. The inferential statistical tools are used in data science as central limit theorem. In a central limit theorem, the mean of the smaller sample is the same as the mean of the larger population. Therefore, the resulting standard deviation is equal to the standard deviation of the population. An important concept of the central limit theorem is the estimation of the population mean. The margin error can be calculated by multiplying the standard error of the mean with z-score of the percentage of the confidence level. Hypothesis testing. Hypothesis testing is the measure of assumption. Using a hypothesis testing, one can attribute the results of a smaller sample on a much larger group. The two hypotheses that we require in this test against one another, the null hypothesis and the alternate hypothesis. A null hypothesis represents the ideal scenario whereas the alternate hypothesis is usually the opposite of it, that using which one can try to prove it wrong. ANOVA. Using ANOVA, one can test hypotheses for multiple groups. It is an improvement of another form of inferential technique called the t-test. Analysis of variance, or ANOVA, is a collection of statistical models that and their associated estimation procedures, such as the variation among and between groups, used to analyze the differences among group means in the sample. ANOVA was developed by statistician Ronald Fisher. The ANOVA is based on the law of total variance, where the observed variance in a particular variable is partition between two components attributable to different sources of variation. In its simplest form, ANOVA provides a statistical test of whether two or more population means are equal and therefore generalizes the t-test beyond two means. ANOVA performs the testing with a minimal error rate. One metric for measuring ANOVA is the F ratio. F ratio is the ratio of the mean squared internally to the group and the mean squared between the groups. Discrete probability distribution. A discrete probability distribution is a probability distribution that can take on a countable number of values. In the case where the range of values are countably infinite, these values have to decline to zero fast enough so that the probabilities all add up to 1. Well-known discrete probability distribution used in statistical modeling include Poisson distribution, Bernoulli distribution, binomial distribution, geometric distribution, and negative binomial distribution. Additionally, the discrete uniform distribution is commonly used in computer programs to make equal probability random selections between number of choices where the set or the sample of observations is drawn from a larger population. The sample points have an empirical distribution with that is discrete and provides information about the population distribution. Continuous probability distribution. A continuous probability distribution is a probability distribution whose support is an uncountable set, such as an interval in the real number line. There are many examples of continuous probability distributions: normal, uniform, logistic, Cauchy, log normal, and Pareto are to name a few. Out of these, the most significant is the normal distribution. In normal distribution, a large number of data samples are represented in a plot. Using normal distribution, we can represent a large variables in a bell-shaped curve, which is also known as the Gaussian curve. This bell-shaped curve is symmetric in nature, meaning the values farther away from the mean taper off equally in both the left and the right directions. For undertaking any inferential statistic problems, it is mandatory that the data is normally distributed. Qualitative data analysis. Qualitative data analysis consists of two important techniques: correlation and regression. Correlation or dependence is any statistical relationship, whether casual or not, between two random variables or bivariate data. In the broadest sense, correlation is any statistical association. Through it commonly refers to the degree to which a pair of variables is linearly related. In statistical modeling, regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called the predictors or covariates or even features. The most common form of regression analysis is linear regression, in which the researchers find the line or a more complex linear combination that most closely fits the data according to the specific mathematical criteria. For specific mathematical reasons, this allows the researcher to estimate the conditional expectation or the population average value of the dependent variable when the independent variable takes on a given set of values. Less common forms of regression you use slightly different procedures to estimate alternative location parameters or estimate the conditional expectation across a broader collection of nonlinear models. Regression analysis is primarily used for two conceptually distinct purposes. First, regression analysis is widely used for prediction and forecasting, where its use has substantially overlapped with the field of machine learning. Second, in some situations, regression analysis is used to infer causal relationships between the independent and the dependent variables. Importantly, regressions by themselves only reveal relationships between a dependent or a collection of independent variables in a fixed data set. To use regression for the prediction or to infer causal relationships, respectively, the researcher must carefully justify excuse me, why existing relationships have predictive power for a new context, or why a relationship between two variables have causal interpretation. The latter is especially important when researchers hope to estimate causal relationships using observational data. The potential learning path of statistics to become a data scientist includes four most important steps. One, learning the core concepts of statistics, like previously mentioned, such as descriptive statistics, distribution, hypothesis testing, and regression. While doing so, it has to be kept in mind that the applications one might need to implement as data scientists, and these can be like experimental designing, regression modeling, and data transformation. Second, applying Bayesian thinking. One of the philosophical debates in statistics is between Bayesians and frequentists. In Bayesian side is more relevant to learning statistics for data science. In a nutshell, frequentists use probability only to model sampling processes. This means they only assign probabilities to describe data they have already collected. On the other hand, Bayesians use probability to model sampling processes and to quantify uncertainty before collecting data. In Bayesian thinking, the level of uncertainty before collecting data is called prior probability, and it then updated to a posterior probability after data is collected. This is a central concept to many machine learning models, so it is important to master. Understanding statistical machine learning. Understanding statistical machine learning is one of the most important steps in order to become a data scientist. In learning statistics for data science, there is no better way of playing with statistical machine learning after being well versed with the core concepts in Bayesian thinking. The statistics and machine learning fields are closely linked, and statistical machine learning is the main approach to modern machine learning. This step will include implementing machine learning models from scratch. This will help unlock true understanding of their underlying mechanics. This will help to break open the black box of machine learning while solidifying the understanding of applied statistics required for the data. Last but not the least, trying various real-life applications of the concept that will help to understand the concepts way better once they are implemented. Up until now, I have mentioned only statistics and data science. Now I would like to introduce big data. The reason for including big data in this session is because it is being regarded as the future of data science. With the access of high-speed internet and the huge storage capacity at our disposal thanks to the development of technology, we have more data than ever before that needs to be analyzed. This calls for better and stronger statistical methods and data science tactics. So what is big data? Big data deals with the vast collection of heterogeneous data from different sources, and it is not available in standard database formats, and we are aware of. This implies that data won't be tabulated into table or chart or graph. Big data classifies data into three parts: structured, semi-structured, and unstructured. While structured data is quite simple to understand, unstructured data requires customized modeling techniques to extract information from the data, which is done with the help of computer tools, statistics, and other data science approaches. The key differences in data science and big data. There are major differences which we should talk about when our topic is data science versus big data. Big data is usually used by organizations to improve the efficiency, to understand the untapped market and enhance competitiveness, while data science is concentrated towards providing modeling techniques and methods to evaluate the potential of big data in a precise way. The amount of data that can be collected by companies are huge and they pertain to big data, but utilization of the data to extract valuable information, in this case, data science is needed. The three V's of big data, guide data set, and is characterized by velocity, variety, and volume, but data science provides techniques to analyze the data. Data science supposedly uses theoretical as well as practical approaches to dig information from the big data, which plays an important role in utilizing the potentials of big data. Whatsoever, big data can be considered as the pool of data which has no credibility unless analyzed with deductive and inductive reasoning. Big data analysis caters to a large amount of data, which is also known as data mining. But data science makes use of the machine learning algorithms to design and develop statistical models to generate knowledge from the pile of big data. Data science focuses more on business decisions, whereas big data relates more to technology, computer tools, and software. This brings me to my next question. Why data science? Data science can add value to any business that can use their data well. From statistics and insights across workflows and hiring new candidates to helping senior staffs make better informed decisions, data science is invaluable to any company in any industry. Companies are applying big data and data science in everyday activities to bring value to the consumers. Banking institutions are capitalizing on big data to enhance their fraud detection success. Asset management firms are using big data to predict the likelihood of a security's price moving up and down at a stated time. Companies such as Netflix mine big data to determine what products to deliver to the users. Netflix also uses algorithms to create personalized recommendations for users based on their viewing history. Data science is evolving at a rapid rate and its applications will continue to change lives in the future. The functional data scientist is opposed to general statistician, has a very good understanding of software architecture and understands multiple programming languages. The data scientist defines the problem, identifies the key source of information, and designs the framework for collecting and screening the data. Software is typically responsible for collecting, processing, and modeling the data. They use the principles of data science and all the related subfields and practices encompassed within data science to gain a deeper insight into data science assets under review. The advantages of data science for business: it helps make better decisions, improve performance, help the staffs follow better practices, helps boost progress through data analytics, identifies opportunities, helps fight competitors, and also helps identify target audiences. Is data science replacing statistics? Data science is more than statistics. It also encompasses computer science and business concepts. And it's far from than than any set of techniques and principles. But when it comes to interpreting data and evaluating the validity of hypotheses, statisticians are the real experts. This expertise will not become obsolete at any time soon. While data science uses a broad skill set to build data products, statisticians use their specialized knowledge to understand data on a deeper level. However, the fields differ in their processes, the types of problems studied, and several other factors. In order to conclude the topic, I think data science and statistics are indistinguishable and closely linked. It is clear that statistics is a tool or a method for data science, while data science is a wide domain where statistical methods is an essential component. Data science and statistics will continue to coexist as there is a big overlap between the disciplines. Also to note, all statisticians cannot become data scientists and vice versa. Data science has developed recently with big data and will continue to grow in the upcoming years as growth of data seems to be never ending. Thank you.
Hello. Thank you, Medhasweta. It was really amazing to hear you a lot about the types of the like names of those statistical domains in different domains like epidemiology, which was popularly used a few months back when people were studying about corona and the cases and the way it was increasing. And I pretty much worked upon some of them, but there were so many which were new to me, and it was really insightful for me. I got to learn a lot of things. And even statistical modeling, hypothesis testing, p-test, ANOVA, probability distribution, these are some of the important aspects that you cover. Do we have any questions? Anyone? You can mute yourself and put on. Hello. Sorry, I was disconnected. Uh, so, do we have any questions in the chat or anyone? I don't see any questions. Thank you, Medhasweta, for taking this up and delivering this session and spreading the knowledge across. Thanks a lot.
Thank you so much for the opportunity as well.
My pleasure. So with that, we end today's session, and there will be the further things will be communicated to you via WhatsApp chat or emails. And I guess that's it for today. Thank you and have a nice day. Have a great evening ahead. Thank you.